Good morning, good afternoon, or good evening, ladies and gentlemen. Welcome to another segment of Unit 3, Biochemistry. Today, what we're going to be talking about are the properties of water. Now, there's a lot of them, some that you probably know, some that you probably don't, but our goal today is to go ahead and talk about the properties of water, what makes it unique, and some specific things about solutions and solvents. Now, without further ado, let's go ahead and get this party started, shall we? So, hydrogen bond. If you paid attention to the last one we did about the intro to biochemistry and basic bonding structures, you would know that a hydrogen bond doesn't actually join atoms together. Nope. Hydrogen bonds are attractions between compounds, so between the more positive and the more negative. Now, they don't actually come together. It's more like, think about, okay, imagine you are the younger sibling, or you have you're the younger sibling yourself, and you're driving on a very long car trip. So your sibling goes ahead over to you and takes their finger, goes ahead and sticks it right near you, but doesn't actually touch. They're like, I'm not touching you, I'm not touching you, I'm not. That's kind of what it's like. So they get uncomfortably close, but never actually touch. That's basically how a hydrogen bond keeps things in play. And as we said before, the most classic example of hydrogen bonding is indeed water, recognized by this right here. So as you can see, the hydrogen, which has a more positive side, is being held in close proximity to the oxygen, which has a slightly negative charge. Positive going to negative, that's a bond, alright. So, hydrogen bonds give water a very unique set of properties. So the first is heat storage. So a large input of thermal energy is required to disrupt the organization of liquid water. This helps minimize temperature changes. And it also has a very high heat of vaporization. So at high temperatures, hydrogen bonds do break, and water is changed into a vapor, resulting in a cooling effect. So compared to other liquids, other compounds here, water. The boiling point of water, if you think back, is about 100 degrees Celsius, which is very high. There are some liquids, like ethanol, that will actually vaporize at room temperature, which is about 32 degrees. So heat storage, a large input of thermal energy is required to disrupt the organization of liquid water. Also, high heat of vaporization when we go ahead and sweat, so our body temperature gets higher and higher. What the water does is the water inside of our bodies actually uses that body heat to go ahead and turn from a liquid into a vapor, taking that heat with it and trying to cool us off. So that's kind of why we sweat, which we'll talk about later on as we progress through the slides here. So heat storage and the high heat of vaporization. So water's heat storage ability allows the temperature of coastal areas to remain more stable. So think about the beach, all right? Everybody loves to go to the beach, summertime. So at the beach, when is the water the most warm? Is it going to be right in the morning? No, not at all. So the sun is going ahead and heating up the water all day. So meanwhile, in the morning, when the sun's out initially, it's very hot outside, right? So what the water does is it goes ahead, and as the sea breeze comes in, it takes that nice cool water and carries it inland, keeping, when it's hot outside, keeping things cool. Vice versa, after, the sun's been out all day and the water's nice and warm, when the sun goes down and it starts to get cold out at night, those sea breezes are going to go ahead and carry that nice, warm coastal temperature and carry it inland, keeping things relatively stable. So these properties, the heat of vaporization anyway, allow water to trap lots of heat and take it away by evaporative cooling, like when you sweat. So when you're sweating, you're going ahead, you're working out, you're running around, your body temperature is going up. So in order for your body to stay cool, remember you don't want to get too hot and eventually, pass out from a heat stroke. That'd be terrible. So what your body does here is the water inside your body goes ahead and uses that heat to change from a liquid to a gas. So it takes some of that heat away. Through evaporative cooling, in layman's terms, this is why we sweat. It goes ahead and it keeps us cool. Now, ice formation. At low temperature, hydrogen bonds don't break. Water forms a regular crystal structure that floats. So what this means is, at low temperatures, the bonds don't break. So liquid, here's basically what's happening to the molecules at the different states. So in a gas, the atoms are flying all over the place. There's nothing holding them in check. In a liquid, they're all held roughly together, but they can still move. Meanwhile, in the solid form, in the case of ice, the bonds that go ahead and hold these things together, the hydrogen bonds, are going to get extremely rigid, which goes ahead and holds it all in a very rigid crystal-like structure that we call ice. Also, the important thing here is it floats. Ice is less dense than water, so ice floats. Now this is super important because it helps prevent bodies of water from freezing solid in the winter and killing off all the life on the surface and underneath. So, in the wintertime, as you can see here, ice will form over the top of bodies of water. Now, underneath the water, we have organisms like fish, maybe some seagrass. But the important thing is, in the wintertime, these things do not freeze solid. What it does is the ice cover kind of creates a little bit of insulation, keeping the water at a constant temperature. So, that goes ahead, protects the outside and the inside. So it keeps the inside nice and warm at a constant temperature for the fish so they don't freeze solid, and it protects them from everything out here. So we're talking about the wind, we're talking about the snow, pretend that's snow, use your imagination. So it goes ahead and protects everything. So, hydrogen bonds give water a unique set of properties continued here. So cohesion. Cohesion is the attraction of water molecules to other water molecules. An example would be surface tension. So that's water's ability to stick to itself. The other type is adhesion. So adhesion is the attraction of water molecules to other polar molecules. And an example of this would be something called capillary action. So as we can see here, in our top example, the water strider uses the surface tension of the water, which allows it to go ahead and stay up on top without falling through. Meanwhile, adhesion, so on the surface of this spider web here, what we've got is we've got water droplets attaching themselves to the polar molecules on the web. Now we're going to be talking about each of these individually, so let's go ahead and get right to that. Oh, by the way, fun science question here. See this little dip right here? What do we call that? What do we call that little dip when we're going ahead and reading something in a graduated cylinder? We call that the meniscus. Anyway, science facts. The more you know. Let's go ahead and continue. So, surface tension. Cohesion. Water to water makes the surface of water like a solid film. And if you're light enough, for example the water strider here, what it can do is it can use that surface tension to go ahead and float. So we have these arms right here that act as paddles, going ahead and propelling it through. We've got these two back here, which go ahead and act more like rudders on a boat. And it's kind of hard to see right now, but there are two arms up here that are used for grabbing prey. So surface tension. Let's go back a bit. Let's say you are going ahead, you are at a pool, right? You're having a great time. You find the diving board, and you get dared to go ahead and do a belly flop. So a belly flop, remember that's where you go ahead, jump off, go basically like this, spray everything out, and come in contact with the water. Now, for those of you that have done this, and I'm sure you have, does it feel good? No, it doesn't feel good. Are you kidding me? It hurts beyond all reason. So what that is a perfect example of surface tension. So the cohesion water to water, when you put that force on it, it turns the water almost into a solid film. So when you come in contact with it, that's why you get that real nice slapping sound. And then the red stomach and the pain and the questions, why would I go ahead and do something like that? I regret. Anyway, so that's basically surface tension, cohesion. So another example here that uses both cohesion and adhesion is something called capillary action, or transpiration. So what is transpiration? That is the movement of water up a plant by capillary action because of the pull from the evaporation through the leaves. So what we have here is a tree. Yep, we got a tree here. Now, up top, as you can see, water is being evaporated through the top of the leaves. We call that transpiration, or plant sweat. So think of this like a giant straw. As water is leaving through the top, we need something to replace that. So up through the roots, we have water being absorbed. So it's one big lengthy process where basically through the process of cohesion, water sticking to water, and adhesion, water sticking to other polar molecules, the water can actually be drawn the entire way up to the very top of the tree. That's what allows plants to go ahead and get most of their water. It's pretty cool if you think about it. Now, water is a great solvent. It's a great solvent because it dissolves mostly everything if you give it the time. So in this section, we're going to be talking about hydrophilic and hydrophobic substances. So hydrophilic means water loving. Hydro, water, philic, loving. And these substances are polar. Now, what does polar mean? That's right. Polar means we have a difference in the charge. So think water. We have a negative and two positives. So hydrogen bonds with water. An example would be sugar. If you go ahead and dump sugar into water, and you go ahead and you give it a little stir, what happens over time? That sugar is going to go ahead, bond with the free-floating hydrogen, and disappear. The other type is hydrophobic substances. Hydro meaning water, phobic meaning fearing. These are nonpolar, and doesn't matter how much you go ahead and mix them, the two will not combine. They are repelled by water. And an example of this would be oil. Hello there. What we're going to be doing now is I'm going to give you a brief demonstration of hydrophobic and hydrophilic substances. So remember, hydrophobic is water fearing, the two won't mix, whereas hydrophilic means water loving, and the two should go ahead and make a homogeneous mixture, or it'll disappear. Remember, hydrophilic, polar, hydrophobic, nonpolar. Polar will mix, nonpolar won't. So, what we have here is we have a little bit of salt and a little bit of water. So what we're going to do here is I'm going to go ahead and dump some of the salt in the water. So, let's see what happens. There we go. Yep. I'm going to get all Bill Nye on you for a second. Using the great spoon of science, we're going to go ahead and mix this stuff together. Now, if this is a polar substance or hydrophilic, the salt should disappear. So if you go ahead and take a look, I'm not seeing any salt. However, I guarantee you it's still in there. Still there. Ugh. All right. So that is a hydrophilic, water-loving. Now let's talk about hydrophobic. So what we've got here is another cup of water, and we've got some olive oil. So this is hydrophobic, meaning non-polar. So the two shouldn't mix. Let's go ahead and see what happens. So as you can see, what's happening here is the oil is floating up on top of the water. But let's go ahead and mix things up a little bit using the great spoon of science to see if we can go ahead and get these two to mix. Now that looks pretty cool, right? It's like a little tornado of oil. Oil-nado. It's the next sci-fi original movie. So as you can see here, we went ahead, stirred things up a little bit, and sure enough, the two separated back out. There was no mixing. Yeah, I'm not drinking that. Sorry. So that was a nice little demonstration of hydrophobic and hydrophilic substances. Let's go ahead and move on, shall we? So, a solution, or a solute plus a solvent, gives us a solution. So we need two parts, right? The solute, these are the solid particles that dissolve. The solvent is what causes the dissolving. So the solute is what's being dissolved, solvent, what's doing the dissolving. And a solution is a homogeneous mixture made from the solute and solvent. So that means we can no longer go ahead and separate the two. Think about like when you're making Kool-Aid. That's the best example I can give you for this. So solute would be the Kool-Aid powder. Solvent would be the water. So the solution would be the fully made Kool-Aid. You can't go ahead and separate the powder back out. So we have two types of solutions. We have a concentrated solution where there is more solute than solvent. Now back when I was a kid, this is how I made Kool-Aid. I would go ahead and pour in way more powder than you actually needed so it would taste all nice and sugary. So there is more Kool-Aid powder than there is water to go ahead and dissolve it all equally. So you might have little bits and pieces of powder still floating around in there, which, in my opinion, back when I was a kid, I thought it made it taste better. Meanwhile, we also have diluted. So diluted is when you have more solvent than solute. That's how my parents like to go ahead and make Kool-Aid. They'd pour more water in than they would the Kool-Aid powder. So it looks all nice and delicious and, you know, a bright red color. But when you go ahead and taste it, it just tastes like water. Red water. And there's that empty feeling of, I've been cheated. I've been bamboozled. Well, anyway, that's enough about little trips down memory lane. So remember, solvent, what causes the dissolving, solute, what is dissolved, and solution is the mixture between the two. So solute plus solvent equals solution. So we do have a little demonstration for you here. So what we got? Water. And what we also have is we got a little bit of peach tea. So if we go ahead and put these two together, we should have a solution. So solute, solvent, here we go. Let's do some science. So we go ahead and we pour that in there. As you can see, it's not fully mixed yet. So we go ahead and give it a little stir. And just like that, let you go ahead and take a nice little look at this. We can't go ahead and separate the two anymore. They have been completely combined. There is a homogeneous mixture of solute and solvent. And it tastes delicious. That's some good tasting science right there. So the pH scale. Last thing we're going to be talking about today. The pH scale measures the hydrogen concentration of a fluid. So, a change of 1 on the scale means a 10 times change in the hydrogen concentration. So let's start off with, just going to go ahead and put that away for now. Let's start off with pure water, or human blood, which is a 7, which is neutral. Equal amount of hydrogen and hydroxide, or equal between acid and base. So up top, as we go down the scale, anything between 7 and 0 is an acid. Anything between 7 and 14 is a base. So, what that means is acids have a very high hydrogen concentration, but a low pH. Bases, on the other hand, have a low hydrogen concentration, but a high pH. So, like I said before, let's go back to the example with pure water, and let's go with urine. So urine has 10 times the amount of acidity of pure water. Black coffee or rainwater, we multiply that by 10 again. So that would be 100 times the hydrogen concentration. Tomato juice, 1,000. And so on and so forth. So every time we go up, we're multiplying it by 10. Every time we go down, we are dividing it by 10. Now, buffers. Buffers are incredibly important. Buffers are substances that can resist pH changes. Now, this is very important. We have these inside of our body to keep things stable. Can you imagine what would happen if we didn't have a buffer? What a buffer does is it goes ahead and nullifies either the acidity or the base of whatever we put into our body. So let's say on a dare, somebody told you to go ahead and drink lemon juice. So if you didn't have this inside your body, you would go ahead, drink a lemon juice, and then slowly you would feel this burning sensation, which would be your own windpipe slowly dissolving. Not a pleasant thing. So buffers keep things inside of our body stable. What's that word we use for it? Oh yeah, homeostasis. One of the characteristics of living things. So acids and bases. Acids. These substances cause water to release hydrogen, meaning they have a high hydrogen concentration. So acidic solutions have a pH below 7. So the big thing to remember here is acids. They have a high hydrogen concentration, but a low pH. Bases, on the other hand, these substances grab hydrogen from the water, leaving behind OH ions. And basic solutions have a pH of above 7. So bases have a low hydrogen concentration and a high pH. Boom. So, once again, that brings us to the end of this slideshow. I'd like to go ahead and thank you all for joining us today. And just in summary, what we've talked about are the unique properties of water that help allow things on Earth to go ahead and remain stable, such as high heat of vaporization, heat storage, cohesion and adhesion, and also its ability to be the universal solvent, or what dissolves things in nature. So, if you have any questions, please go ahead, bring them to your teacher. And until next time, I will see you in the next video. You all keep it classy.